Uh, this class we are going to discuss a new concept, which is something called stagnation quantities or stagnation concept. So, if I have a flow and if I measure quantities while traveling along with the flow, what I would be getting is something called static quantity. So, if I have a flow with velocity, some velocity of the fluid, and if I travel along with the fluid with the same velocity and measure my temperature or my pressure, I call those quantities as static pressure or static temperature, and hence other quantities measured like that, if they are measurable. So, we need a reference quantity, which is now we call as stagnation. So, what do I mean by stagnation quantity? So, if I have a fluid with velocity v, with some velocity, and if I bring that fluid to rest at without losses and with no heat or work. So, if I bring the velocity of the fluid to 0 with no losses or no heat and work. So, I am bringing the fluid isentropically to 0 condition. So, graphically, if I have a point here, so let us consider this as TS plane. I have a state 1 here, the velocity at that particular point or at that particular state of the fluid is some v. Now, I am bringing this fluid to 0 velocity without any losses, which means it is isentropic process. So, it would be a straight line somewhere here and with no heat or no work done. Okay. So, this is my say 0 condition, the stagnation condition. So, let us go back to the equation and see how it behaves. So, we have dq or delta q equals dw s plus your dh. Okay. So, if this condition is my state A and this is my state B, I would have HA plus VA square by 2 plus G ZA plus Q equals WS plus HB plus VB square by 2 plus G ZB. Now, what did I assume? I assume no losses isentropically and no heat, no work. Okay. So, I have no heat, no work, and I have brought the velocity to 0. So, my V 0, and I do not have a potential difference between these. The potential energy is also brought to 0. Okay. So, my HB is HA plus VA square by 2 plus G ZA. So, let us assume flows without the potential energy, which means the quantity is also assumed 0 for most of the cases that we are going to discuss in this course. So, let us just stick with the kinetic energy. So, the enthalpy of point B, where I have brought my fluid to rest isentropically, is given by this. So, I call this as my stagnation enthalpy, which is typically denoted as 0 into h plus v square by 2 if I consider any point. Okay. So, any point here is brought to rest at some point here as the stagnation point. So, any point associated with any point, there is a stagnation point if I do this process. I bring back the velocity to 0 isentropically. Okay. So, this is my stagnation enthalpy. If that is the case, I can rewrite my original equation, say for example for 1D flow. In the previous lectures we have seen between two points or for the process 1 to 2, I have written h1 plus v1 square by 2 plus q equals h2 plus v2 square by 2 plus ws, okay, which means I have a process 1 to 2 in the TS diagram. I have a process 1, I have a process state 2, I have a process that is happening between 1 to 2, and the energy is related in this particular fashion for 1D flow. Associated with 1, there is a stagnation point, associated with 2, there is a stagnation point. Okay. So, I can rewrite this as h01 plus q with h02 plus ws. So, h01 is the stagnation point associated with point 1 here, this is 01, and h02 is the stagnation point associated with point 2. So, if this is 2, this is 02. Okay. Now, between these 2 points, h01 plus q equals h02 plus ws. If no heat is applied or no shaft work, you get this term and this term 0. Okay. So, if there is no heat supplied in the process 1 to 2 and no shaft work, so the q is 0, ws is 0 in this process. If that is the case, then I can strike off this, which essentially mean h01 equals h02. Okay. If this is true. If the gas is a perfect gas, for a perfect gas, I can rewrite this as Cp T01 equals Cp T02 or T01 equal T02. Okay. Which means in the diagram Ts 0.1, 0.2. My stagnation temperatures are same. So, the stagnation temperature associated with the state 1 is same as stagnation temperature associated with state 2. So, these are same. Okay. So, remember there is no Q and no Ws. Shaft work is 0, the heat supplied or heat transfer is 0 for this to be valid. So, if I have a nozzle flow, the gas has, if I have a nozzle, flow is from this side, there is no Q, no Ws. In such a scenario, I can assume this. Okay. But if I have a propeller here, I cannot assume this. That is the meaning of constant stagnation temperature. There is no loss in stagnation temperature. So, this T01 or the T0 is called your stagnation temperature or your total temperature. Okay. Now, consider process from 1 to 2 where there is no Q, no Ws. So, my T01 is same as T02, this is 1, this is 2, my Q is 0, Ws is 0. Okay. Now, let us see if let us see what's P01 and P02. So, associated with the static state, I have a static pressure, and now I have defined a reference quantity which is a stagnation quantity. So, along with T01 I have a P01, and same as for the second state I have a stagnation pressure. Okay. Let us see what happens to P01 and P02. So, I start from my Gibbs equation, Ts equals dH minus V dP. Now, I am talking about stagnation quantity. So, this is my T0 ds0 equals dH0 minus V0 dP0. Okay. Now, the ds associated with this is same as the ds associated with these 2 points. Okay, from the picture, from the graph. So, my ds is same as ds0. T ds0 dH0 minus V0 dP0. Like before, I split my ds into ds reversible plus ds irreversible equals dH0 minus d0 dP0. From my energy equation, I have dq equals dws plus dh plus dv square by 2. Okay. Or I can write this as ws plus dh 0. Now I substitute this quantity here. Okay. So my dq equals dws plus t0 ds reversible plus ds irreversible plus u0 dp0. So I am substituting this here. So I have taken the energy equation and from the Gibbs equation I have substituted that. Okay. So use V0, which is a specific volume, I can rewrite this as rho 0. So that's the stagnation density associated with some state, plus T0 ds reversible plus ds irreversible plus dws minus dq. Now dq I can replace as my ts reversible from the second law of thermodynamics equals 0. So I have taken the Gibbs equation, I have taken the energy equation, substituted the stagnation enthalpy change from Gibbs equation into this, and I have replaced dq with T ds reversible from the second law of thermodynamics. Okay, that's all I have done. Now let's look at this equation. So your change in stagnation pressure depends on the irreversibility, the losses, the heat supplied, which is your d reversible, and your shaft work. Okay. Okay. So I write this plus T0 minus T reversible plus T0 ds irreversible plus dws equals 0. If no shaft work, ws is 0, no heat input, so my second term is 0, d reversible 0. So what is left is dp0 by rho 0 plus t0 d irreversible equals 0. Now rho 0 or T0 is my P0 from my ideal gas equation. So I substitute rho 0 here, I should get dP0 by P0 0 plus ds irreversible by R equals 0. So, how do I represent this equation graphically? So, between two processes, if there are no losses, your irreversible is your losses. So, if there are no losses, dp d0, this is going to be 0. So, between these two processes, losses ds irreversible is 0, which means in the picture here, from process 1 to 2, if there are no losses, there is no entropy change. So, ds, this quantity is going to be 0, which will lead to this equation, which essentially means P0 equals constant. Or I redraw this picture. Okay, Ts. State 1, it just means there is no entropy change. So, I have state 1, I isentropically take it to state 2, so that there is no loss, there is no shaft work, there is no heat input. So, from 1 to 2, I take the state from 1 to 2. Associated with 1, there is a stagnation point. Associated with 2, there is a stagnation point, which we have seen both are same if there is no shaft work and no heat input. So, your T01 equals T02. Now, this also tells me my P01 equals P02. Okay. But if there is losses, it is not equal to 0, what do? I need to integrate this. dp0 by p0. So, if there is losses, if there is some loss due to friction or some heating, you need to integrate this equation. So, I integrate dp0 by p0 plus d as irreversible by r, okay, equals some value or some constant. Or I can take it to the other side. Okay, so this would be ln P02 by P01. This would be delta S, which is S1 minus S2 by R with a minus sign. Okay. So, if this is, if I take the exponential, P02 by P01 is exponential delta S by delta R. This also means something. So, I rewrite that equation here. P02 by P01 equals exponential minus delta S by R. So, all your P0 change is due to your irreversibility condition, given that there is no shaft work, there is no heat input. If those two conditions are satisfied, the changes in P01 and P02 is entirely due to your irreversibility or the losses that is happening in the flow. So, if delta S is always positive, okay, which means your P02 is less than P01. Okay. So, if I have a P01 here, this pressure is less than this pressure. If there are losses. If losses. So, I repeat what we had learnt today. So, what I want to do here is, so I have a state 1 which I bring it to a quantity with 0 velocity where v is 0. I have defined my h1 to be h01 to be h1 plus v square by 2. This is what we have seen in the earlier part of the lecture. Now, for perfect gas, this is Cp T01, this is Cp T1 plus V1 square by 2. For any process, I can remove the suffix 1, okay, for any state. So, my T0 is T1 plus V square by 2 Cp, okay, or my T0 minus T is V square by 2 Cp. So, this difference here is just V0 by 2 Cp for a perfect gas. So, I have a flow in which I take the condition, the static condition, to a stagnation condition, meaning I take the flow to a 0 velocity isentropically with no heat and no shaft, then the difference in temperature is given by this quantity V0 by 2 Cp. Okay. We are going to have few other reference quantities and we will see where they are placed in the TS diagram. What we have learned today is the stagnation concept of stagnation condition, the possibility of a new quantity, a stagnation temperature, and associated with it you have a stagnation pressure, and hence other quantities as applied to your energy equation as well as your ideal gas equations. So, those are related, the relations are derived from your again from your thermodynamics laws and energy equations and your Gibbs relations. So, for a case where there is no heat and no shaft work, if the process do not involve losses, you have T01 equals T02, the stagnation temperature at for a state associated with 1 is same as your stagnation temperature associated with state 2 if they undergo a process without heat, without shaft and no losses. And we have also seen how the stagnation pressure changes and why irreversibility is affecting the stagnation pressure. So, the difference in temperature, stagnation temperature and static temperature depends only on your velocity and the kind of fluid that is undergoing. Okay. So, that is the final message from the lesson, where the difference in your stagnation temperature, difference between the stagnation temperature and static temperature is just your kinetic energy and the associated fluid property. We will try to see what the constant density would bring in the relation of stagnation quantities. So, what is stagnation pressure for a constant density fluid? What is stagnation temperature for a constant density fluid? Okay. So, we start with Gibbs relation, TdS equals du plus Pdv. Okay. Constant density fluids. So, that is the topic of this short lecture. So, if we are going to deal with the stagnation quantities, we write this. So, if it is a constant density, density is inverse of your specific volume. So, your d rho is 0 and hence your dV is also 0 for a constant density fluid. So, if I put that here, I would lose my second term on the right hand side. Okay. So, my TdS is du or the T0 0 is d. Okay. Now, if this is the case, my stagnation process is isentropic, okay, which means my ds is 0. So, if my ds is 0, my du is 0. So, for a constant density fluid, my u0 is Cv, du0 is Cv d T0. So, if du 0, my dt is also 0. If du is 0, my dt is also 0. Okay. So, my du is 0, my dt 0 is 0 for density constant fluids, for a stagnation process where my ds is 0, for the stagnation process. Okay. Which is also true if I write du is 0 and dt is 0. Okay. Essentially, it means for constant density fluids, my u equals u0 and t equals t0. There is no distinction between stagnation and static quantities for a constant density fluid. That is what it means, because the stagnation process is essentially isentropic, and if you substitute that in Gibbs relation, you directly get the inference as static quantities same as your stagnation quantities for u and t. What about P? My definition of enthalpy is u plus Pv and dH du plus P dV plus V dP. Now, dV is 0 for a constant constant. We have also seen du to be 0 for or equals constant fluids if if the fluid is undergoing a stagnation process, meaning I am taking the fluid to a state where the velocity is 0 and the process is isentropic with no heat and no shaft work. Okay. So, I am left with dH equals V dP. dH is H2 minus H1 equals V into P2 minus P1. So, the stagnation process, my two is 0 and 1 is no suffix. So, P0 P. Okay. I can replace V as 1 by rho P0 minus P, H0 minus H. Okay. Now, H0 is H plus V square by 2 minus H, okay, equals 1 by rho P0 minus P. So, my H and H cancels out. So, my P0 minus P is 1 by 2 rho V square. So, a constant density fluid undergoing the stagnation process, constant density fluid which has a velocity V is taken to a situation where the velocity is 0 isentropically with no heat and no shaft work, then this relation holds, where your P0, which is a stagnation pressure, minus your P static pressure is 1 by 2 rho V square, which is typically called as dynamic pressure for an constant density fluid. Okay. So, your T is same as your T0, U is same as your U0, but P is not same as your P0. Okay. So, the stagnation pressure minus your static pressure for a constant density fluid is your dynamic pressure. Okay. So, that is a short lecture on constant density fluid, how you can reduce the relations what we learned in the previous lecture to your incompressible flow relations.